morning, everyone. And welcome to the third session of the OSHER at Dartmouth Summer Lecture Series. I'm Pete Blyler, and I will be your session moderator today. First, a couple of housekeeping items. You see the exit signs to my left and right, or your right and left. If there's an emergency, you can exit out there or go out the back the way you came in down the stairs. The second thing is to take your devices and make sure there's silence for the thing, and mine is silence. Hope yours are. And I want to acknowledge and thank today's sponsors. Our season sponsors include the Jack and Dorothy Byrne Foundation, Tim Caldwell and the Caldwell Law, Doyle and Lohman Wealth Management, Kendall at Hanover, and the Village at White River Junction. And today's sponsor is also King Arthur Baking. Can we have a round of applause for our sponsors? And that's good because their support of the Summer Lecture Series means that we can keep the price of your tickets at a reasonable level. I also want to give a shout out to the 3 OSHER programs that are joining us by live stream: the University of Richmond in Richmond, Virginia, the University of Georgia in Athens, Georgia, and UMass Boston in Boston, Massachusetts. As you know, after our speaker's presentation, we will take a 30-minute coffee break. And at that point, bring your questions to the front. We'll have this basket out here to put them in. Write down your questions as the presentation goes on, as they pop into your mind. You can also, there's also a basket in the rear, and you can put them in there. And for those of you on live stream, you can use the chat function to get them here. There will be a post-session discussion in the OSHER office in room 3A from 11:45 to 12:15. When you exit out here on Park Street, take a right, and you go down where 3 Tomatoes, and that's Court Street. Go down Court Street, halfway down is the entrance to the OSHER office, and you go up to the 3rd floor. Again, that's 11:45 to 12:15. Today's session is on climate change, the impact on prosperity. And our speaker today is Virginia Burkett. Virginia is the Chief Scientist for Climate and Land Use Change with the U.S. Geological Society, which is part of the Department of Interior. More information on her background, experience, and expertise is in your program, but right now I'd like to introduce Virginia. Welcome, Virginia.
Thank you, Pete. Let's get these slides up here. Okay, thank you, and thank you so much for inviting me here to speak today at the OSHER Lifelong Learning Institute's Summer Lecture Series. It's truly an honor to speak with you, and I deeply appreciate the hospitality that has been extended to me during my visit. It's my first time in Hanover. It's been very pleasant. I was able to get a glimpse of the campus yesterday, and a feel that I obtained for that rich history and traditions at Dartmouth is, I won't forget that. An iconic academic excellence that this institution represents since 1769. And the college, if you go to the college website, when I was just touring, it claims to prepare its students for a lifetime of learning and responsible leadership. And I think this OSHER lecture series is just an indicator of that commitment. So I'm a scientist with the U.S. Geological Survey, and USGS is a science bureau of the U.S. Department of the Interior. It's the science bureau. USGS has been around not quite as long as Dartmouth, since 1879, 145 years. And we have experts in our 8,000 member staff in every state, and the fields of biology, geology, hydrology, natural hazards. Like if you hear an earthquake alert or tsunami warnings and volcanic eruptions, that's generally from the U.S. Geological Survey. So we do global reporting on those hazards. And we also have this satellites here, the Landsat satellites. When you go to your cell phone and you pull up Google Earth, you know, some of those initial images that you see are coming from our satellites. NASA launches the satellites for us, then we take over the keys after an on-orbit checkout, and we deliver and we dodge debris, all that sort of thing with our Landsat operations team. Landsat, and I'll show you kind of the applications of this satellite in some of my slides. So Landsat, the two satellites, Landsat 8 and Landsat 9, circle the Earth each every 99 minutes in a polar orbit. And so we get an 8-day revisit of every 30-meter pixel, the size of an infield of a baseball field, every 8 days with these satellites together. And these are harmonized with a set of satellites that the European Space Agency has planned in conjunction with our Landsat team so they can be merged together. And we have a 5-day revisit of every point on the land surface. We don't image over water. So that's kind of a little bit about the USGS. We're a fact-finding organization with no regulatory responsibilities, just about the science. As a matter of fact, our motto is science for a changing world. So all those different disciplines coming together to provide science to support decision-making. So before I go any further, I want to thank my host, Ann Hargraves, and Pete and Ruth Blyer. I appreciate the hospitality and the opportunity to speak to you today, and all those in the larger OSHER framework that are online today. I welcome you, and I hope that you feel fluent in talking about climate change and its causes and its impacts. Today, I was invited to speak about climate change and prosperity in this series about American prosperity. And I was asked to focus on sea level rise and other impacts on coastal systems. So here's an outline of my talk. I'm going to present some highlights from the most recent National Climate Assessment, came out last fall, and the most recent IPCC reports. I'm an author of 4 different IPCC reports myself, but these are syntheses of what scientists agree are the synthesis of understanding about climate change and its impacts. So I'm going to provide you with a foundation for understanding basic climate trends and projections and how these drivers of change affect natural systems and human systems with an emphasis on coast. I'm going to talk about sea level rise and give you some examples of impacts observed and projected and adaptation, and then with some messages about what to do, how to respond, and some of the experiences that I can bring to you today, just I think as an encouragement that we are not helpless in this whole situation in terms of mitigation or adaptation, and I'll explain the difference. So I'm going to start here at talking about the difference between weather and climate. And it's just a measure of time. So weather is the condition of the atmosphere at a particular time and place, and climate is how the atmosphere behaves over relatively long periods of time. And typically, meteorological scientists look at 30 years of data or more to determine whether there's a trend in the climate. Okay, so these persist for decades or longer, and this is Hanover. So this is the satellite, excuse me, this is the NASA record of temperature in Hanover, New Hampshire, since 1880. And we have a lot of recording stations around the world and in the United States that go back that far. And in this chart, if you picked just 5 years, okay, you can imagine just picking 1 year, that you would not really get a feel for what the climate is, the long-term trends in the climate are here in Hanover. If you pick this area here, for example, you might have thought that it was going to continue to go up this high. So you have to look at these longer-term trends, and you can see here that the temperatures, the annual temperatures in Hanover have been increasing during this entire period of record, if you do a regression through this, since the early 1990s. And the black line there shows the corrected effects for the urban environment where the station is located. And again, and all of my references here, I will show you exactly where they came from. And if they're a photo and it doesn't have a reference, it's probably my photo of the coast. So first, let's talk a little bit about the greenhouse effect. And the climate of the United States and the Earth in general is determined by the interactions between the sun, the oceans, the atmosphere, the land, and even living things like forest and diatoms. So solar energy enters the atmosphere, the top of the atmosphere, as shortwave radiation. And some of this energy is absorbed by the Earth's surface, and then the remainder is radiated off the Earth's surface back into the atmosphere as longer wavelength heat energy that has a harder time getting out of the atmosphere than that shorter wavelength energy would. So the atmosphere of the composition of the atmosphere is very important because these gases here determine the amount of radiative, the heat energy that is absorbed as that long wave radiation reflects back off the Earth. And the atmosphere warms, it reflects, radiates heat back to the surface, and of course all that together is called the greenhouse gas effect on temperature. And let's see if I can get this working here. So, I wanted to mention here also, so this is the incoming radiation. This is in watts per meter square of solar radiation, that yellow incoming at 340 watts per meter square. Then you can see that it's reflected back off the Earth's surface as that longer wave radiation. But the interesting thing about this graphic, and the IPCC has one that's even slightly higher, 0.6 watts per meter square is the influence of human activity on the Earth's surface, on the atmosphere. And so that green arrow there is the global energy imbalance that implies that one can expect additional warming before the Earth's climate system attains equilibrium with the current levels and concentrations of radiative forcing. So that's a tiny bit, but that's you're experiencing, and you'll see the effects of that tiny bit of imbalance. So to give you a perspective, probably many of you are exercise, walk, run. You know, I used to be a runner, and just knowing that I could run to the top of 75% of the mass of the atmosphere in just a few hours maybe, that's how thin it is. It's a very thin sheet of air extending from the Earth's surface to the edge of space. And when you're looking vertically at the Earth's surface, and you see like a hurricane or a weather system, you get the impression that it's much thicker than it is. At least I did when I was younger. And in this picture here that was taken from space by NASA about 200 miles above the surface, you can see the atmosphere is a very thin blue band between the surface of the Earth and the blackness of space. If the Earth were the size of a basketball, and I was holding it here, and you wrapped a piece of plastic wrap around it, that would be basically a good representation of the thickness of the atmosphere. So it's very small relative to the diameter of the Earth. So how do we know climate is changing through time? We use ice core records and a lot of other paleo evidence, pollen and sediments and lakeshore history and that sort of thing, to determine how the temperature and the sea level have changed through time. I'll focus on temperature here. That's a colleague of mine, Lance Gorham, doing a tree ring analysis. And so you've got the tree ring on the top of the brown, and then you've got an ice core record on the bottom there. And just comparing, so you know where the summer ice is and the winter ice, and you can, the winter ice is dark. And so we have the National Ice Core Laboratory that we operate with funding from the National Science Foundation. And so our scientists take these ice cores under constant temperature and pressure, then they extract the water and the air and the pollen and that sort of thing. And we can determine very accurately what the CO2 was 300,000 years ago in that ice core. We can also look at the isotopes of the oxygen and the hydrogen atoms, or the molecules, and determine very precisely what the temperature was when that ice was laid down. So here's an ice core record from Vostok, Antarctica, here. And it shows very nicely that the history of temperature and CO2 levels. And you have, of course, naturally occurring warm periods and ice ages in the Earth history, shown here. So this is the CO2 concentration is in the lower red line. And you can see it doesn't match perfectly, and I'll explain a couple of reasons in a minute. But this is the important thing to me as a coastal ecologist. And this is the Holocene epoch. This is the last 10,000 years. And see how stable this period was in the Earth's temperature? Well, look where we are now. I'm not implying that temperature is going to go up dramatically like that. There are a lot of buffers in the system. But as a result of human activity, there are an additional 1.5 trillion tons of CO2 have been emitted to the atmosphere since the pre-industrial era. And CO2 levels are now comparable to what we had in the Pliocene between 4.1 and 4.5 million years ago. So in 2023, global greenhouse levels, CO2 levels in the atmosphere rose to 419 parts per million volume. That means that there are roughly 50% more carbon dioxide molecules in the air today than there were in 1750, the year 1750. But you can see the Earth's climate has changed many times over the past, and here we show just the last 4 glacial cycles. So all those other blips in that temperature record. There was a Serbian physicist, mathematician, Milankovitch, and if many of you are probably familiar with the Milankovitch cycles, and he posited that there were changes in the Earth's orbit around the sun that accounted for that 100,000 year scale trend in warming and cooling, ice ages and warming periods. And these are the 3 cycles that he suggested and that scientists publish about today, including the most recent IPCC reports. So the Earth goes in roughly an elliptical cycle in its orbit around the sun to a more circular cycle, elliptical circular. In the elliptical end of things, or trend in the orbital cycle, the Earth gets less radiative forcing, and so you have the ice ages occur. The Earth also spins on its axis. I'm a pilot, and I had an old Cessna. I would have to reset that gyro constantly because it would precess. Basically, the Earth does that on its axis, and that's called precession. And precession occurs in a period of about every 26,000 years. And then we have the Earth actually tilting on its axis as it goes around the sun, and that's called obliquity, and that's a 41,000 year cycle. So all these together, they're not synchronous, and it helps you understand some of those blips other than the 100,000 year scale warming and cooling that I showed you in the last slide. So these connect the geological record of past ice ages and warm periods with the geology. So today, we'll start with a few basics. I think it's important to understand greenhouse gas concentrations and the causes. And here on the left, you've got an IPCC a quote in the middle, and that graphic is actually from the prior 2014 report. I think it's really easy to understand. So you've got the CO2 measurements in green. The next most important gas is methane, and then nitrous oxide. So these 3 gases, and you can see when human activity started to affect their concentrations, the industrialization that we've experienced and have contributed to these increases in greenhouse gas concentrations. Methane and nitrous oxide concentrations are at their highest in at least 800,000 years. And we did this in 150 years or less. The graphic on the bottom right here is also from IPCC, and I like it because it's so simple. It shows the primary contributions, where they come from, and the gray area there is, of course, fossil fuels, as you can see here. And then you have forestry and other land use, which is the second big component of greenhouse gas emissions. Methane is important because methane it has a greater radiative forcing potential. It warms more than 80 times the warming power of CO2 over the first 20 years that it reaches the atmosphere. It's a shorter-lived atmospheric gas, but the impacts are really important. I took this photo here on the right on Saturday, where I live in Louisiana, and we've got two of these big flares going. And this is called flaring, and that's part of that gray area there in the graphic. And so flaring ends up releasing both methane and CO2 into the atmosphere. And I have a couple of bright spots. British Petroleum has announced that it will eliminate all onshore routine flaring in the United States by 2025. So there are, and zero routine flaring in the U.S. onshore operations by the end of the century, by 2025. And then they have a net zero aim as well. And the other thing that I think people say, well, what about cement production? Why is cement even mentioned as a greenhouse gas source? Well, cement production emits CO2 from the calcination of limestone. And cement production is also highly energy intensive. The cement industry is currently responsible for 5 to 8% of global anthropogenic CO2 emissions each year. And China is remarkable in the amount of CO2 emissions from cement production. Oh, that's just that flare. So human influence has warmed the climate at a rate that is unprecedented, and it lasts the least 2,000 years, and this is from the most recent IPCC, and I'm sorry for the acronym. The IPCC is the Intergovernmental Panel on Climate Change, and it is hosted by the United Nations Framework Convention on Climate Change and the World Meteorological Organization, WMO. They have based in Geneva, Switzerland, and they organize these assessment reports every 6 to 8 years. And so this is a graphic from the most recent summary for policymakers, and you can see here changes in the global mean surface temperature back 2,000 years. So this end of it would be, this end here would be reconstructed from the paleoclimate record, as I mentioned before. High confidence in particularly in the ice core records. And the black line there is the actual observed trend here. So this is the actual record from instruments that have been observed globally. So these changes in global surface temperature are shown here on the right, and people will often say, well, what about volcanic activity? What about sunspots? I was told I need to speak up a little bit, I'm sorry. So the IPCC basically accounts for those sorts of natural variability. And this is the observed trend, and this is what it would be without human activity, shown here in the blue frame here, or the blue shaded area. So this is the observed change since 1850 to 2020. Human activities, with no doubt, are the primary driver of the recent global temperature rise. There's no evidence, according to our national climate assessment with hundreds of authors and the IPCC, there's no evidence that natural variability can account for these trends that we've seen, or that the natural volcanic activity or solar activity can explain the changes there shown in the red bar on this histogram. So global temperatures are rising in response to the changes in greenhouse gas concentrations, unequivocally. The global average surface temperature has increased 1.1 degrees Celsius since 1850. That's about 2 degrees Fahrenheit. Some places are warming faster than others, though, as I'll show you. And generally, the higher the latitude, the more intense the warming. And part of that has to do with the changes in albedo, the reflection off the ice and snow, and the decline in snow cover is an important driver in places like Alaska. But as you can see, the warming in the globe and in the United States is not uniform. So when you're talking to a policymaker, it's important to understand that some places are warming faster than others, like Alaska, interior Alaska here, 7 degrees increase. It's just remarkable that variability, and you have to look at an individual place to determine what the trends have been. So, but one thing for sure is that the world is warming faster than any time in at least the last 2,000 years, and each of the last 4 decades has been warmer than any previous decade since 1850. So let's just focus on the United States with this graphic here from our National Climate Assessment from the U.S. Global Change Research Program, which is 14 plus U.S. Federal science agencies like NASA, NOAA, USGS, and others. So here we have the global temperature record in the black, and we have the U.S. temperature records in the blue. And the continental United States, CONUS, originally the records go back to 1895, very strong instrumental records from the continental United States. And then we brought in Alaska with the records and the stations reporting there. And then all of the other Hawaii, Puerto Rico, U.S. affiliated islands all come into that all U.S. trend there. So you can see it tracks pretty well with the global average. Let's look at New Hampshire. Okay. So the greatest warming in New Hampshire has occurred in the winter, and your impacts on snow cover and the milder winter temperatures. And of course, winter temperatures and extreme events, those are the ones that structure your plant and animal communities. So you may have seen changes in the distribution of maple, for example. And so the changes in the number of warm summer nights, shown up here on the upper left, warm summer nights, and then the lower one, these two are for the lower 48 states here, contiguous US, and the top 2 figures are from New Hampshire. And this is from the NOAA State Climate Summary that I'll reference several times in my talk. So this goes back to the period of record here in New Hampshire, and you can see an increase in the number of warm nights and a decrease in the number of very cool nights. These cool nights are where you have a minimum temperature of 0 degrees or lower. I've heard stories from several of your alumni at Dartmouth about going to school here and the terribly cold weather, the minus 28 Pete was mentioning earlier when he was a student that he experienced walking to class. So you can see and look at the difference in the scale here. So this is 40 days difference, and for the United States, the scale is half that. So this, if you use the same scale, it would even appear larger. So this is the mean across, the black line across the center is the mean, and this is the annual average, the annual number of very cold nights decreasing through time. It's remarkable. So again, the higher the latitude, the more striking the increase in the temperature and the decrease in the cool temperatures. And these are 5-year periods, I'm sorry, not annual, 5-year periods. So for New Hampshire, looking to the future, the temperatures in New Hampshire have risen more than 3 degrees Fahrenheit since the beginning of the 20th century. 3 degrees. And remember, for the country, on average, it was, globally, it's 2 degrees roughly. So under a higher emissions scenario, historically unprecedented warming is projected during this century. And warming here has increased more in the winter than in any other season. And future warming will have large effects on snowfall and snow cover. And I'm sure you've probably observed some of that in your lifetime. So as the temperature of the atmosphere warms, of course, the surface of the oceans exposed to those higher heat, and we've seen an increase in ocean temperature. And this is a graphic that you can download every year from the EPA that shows the sea surface temperature globally through time. And again, that black line across the middle is the average here. So it's compared to this 1971 to 2000 year average. In addition to just the overall warming, there's been a change in the marine heat wave occurrence. Marine heat waves globally have doubled in frequency, high confidence according to IPCC, and have become more intense and longer. All right, so that's the global. And here's the cumulative intensity of marine heat waves along the US coast. And a marine heat wave is defined as a period of at least 5 days in a row in which the sea surface temperature at a given location is hotter than it was in the 90% of the past observations at that location. And you can see again how the higher the latitude coming into New Hampshire, the more intense the warming has been. As the atmosphere warms, it causes an exponential increase in the evaporative demand in the atmosphere, call it vapor pressure deficit, and it's the difference between the amount of moisture in the air and how much moisture the air can hold when it is saturated. So globally, we've seen an increase in precipitation over land, and the faster rate of increase since the 1980s. We've seen an increase in the intensity and frequency of heavy precipitation events over land, very high confidence there. And as the climate has warmed, extreme precipitation events have become more intense and make up a larger fraction of total precipitation, while the moderate events become less common. So you can see this trend here from our 4th National Climate Assessment, and I'll show you a more recent one just through time. So we're getting more precipitation, but it's coming down more in the form of heavy downfalls. So those contribute to flooding. They're not as effective in maintaining soil moisture for agriculture, forestry, and runoff to your coast. So here's a graphic from our most recent National Climate Assessment, and you can see that we're going from the present day climate to more extreme events, basically. Less moderate precipitation in the past compared to more extreme precipitation in the present and future climate with warming. So that moist inflow of water into the atmosphere accounts for this change in the intensity of precipitation. Let's look at New Hampshire. So observed annual precipitation in New Hampshire since 2005, if you just consider 2005, it's about 7 inches higher than that average shown here in this line across your historical record. That's 1900 and 2014. So in addition to the increase in the total precipitation for New Hampshire, there's also been an increase in the observed intensity of precipitation events, or the increase in the extreme precipitation events. So these bars here on the left are these 5-year averages in extreme precipitation events. And that's of 2 inches or more per day. And that's between 1950 and 2020. The dots are the annual values, and the bars are the averages over the 5-year periods. And compared to the U.S. average, look at how much stronger that signal is here. The U.S. average is on the lower right. So as the atmosphere warms, I've talked about precipitation change. Another consequence is the decline of glaciers globally. I like this graphic from our 2014 IPCC report. And you can see this is the loss. This is not an increase in glacier mass. This is the loss of glacier mass through time. And you can see glaciers and in the ice sheets, a loss of that land ice. Ice sheet melting has accelerated in recent decades, increasing their contribution for Greenland since 1916, 22%, from 13 to 22%, and for Antarctica from 7 to 14% since 2016 compared to 1971 to 2018. So that's the Greenland ice sheet change. And you're talking, the amount of water in the Greenland ice sheet equates to 7 meters of sea level rise. Fortunately, it's not happening, it's happening very slowly, and we call it latent sea level rise. It will continue for centuries. So this sea level rise is a consequence of warming that is caused by thermosteric dynamics, the thermal expansion of seawater as it warms, very simply, physical change. And the second contribution to the increase in ocean volume is this transfer of water from glaciers, ice caps, and the Greenland and Antarctic ice sheets. So our U.S. National Climate Assessment and IPCC, the general consensus of the rise of sea level by 1 to 4 feet by 2100, but it depends upon the changes in the greenhouse gas concentrations. It's possible that could get to 8 feet by 2100, physically possible, although we cannot assess the probability of that. And again, it depends upon the emissions. So this is the projected global sea level rise. Oops, excuse me. Keep hitting the forward button. So this is the historical rate, and these are the projections into the future under different pathways, shared socioeconomic pathways that are used to model or lay out plausible futures. And the warmest is this 8.5 watts per meter square increase, and the cooler scenarios are shown down here, SSP 1 with less than a quarter of the radiative change, forcing change that you would have in this higher emissions scenario. So it depends on the emissions as to what the future sea level rise will be. And the confidence, medium and low confidence is ascribed to, when I say likely or very likely, both the IPCC and the U.S. government through our U.S. Global Change Research Program, we have a lexicon that scientists use to try to explain and communicate the likelihood of climate projections into the future. So in the United States, focusing more on our country, these are the historical changes in relative mean sea level. What is happening here is that some places are sinking, like coastal Louisiana and Texas, even parts of the Atlantic coastline. And so the rate of sea level rise appears to be higher, but part of that is due to the land sinking. So the coast, doesn't matter to the coast, it's going to respond to that elevation of the water with respect to the landforms. And in Alaska here, this is interesting. So we have actually a decrease in mean sea level. And that's because the land surface is rebounding since the retreat of the Laurentide ice sheet during the last glacial maximum. And so it's like a balloon, the surface of the Earth, these crust, is floating on the mantle. And when you press down in one place with the weight of an ice sheet, it balloons up in another. And so as the ice sheet retreated, you see this, the sea level at the coastline being affected. And this is just the relative change. And so everything in the yellow and the red is an increase in mean sea level, or relative sea level, and everything in blue here is a decrease in the rate of sea level rise. Globally, the rate of sea level rise has almost tripled over the last century. It's currently about 4 millimeters per year. When I worked on my first IPCC report and my first national climate assessment, the rate of sea level rise was 1.7 millimeters per year. And if you had told me then that it would be 4 millimeters per year today, I would have said low confidence or unlikely. I think most of us and we're conservative as scientists, and these rates of sea level rise that are now recorded very accurately with satellite altimetry are remarkable. Sea level rise projected into the future, shown here under a low scenario of 0.3 meters, intermediate low 0.5 meters, and then up to 1 meter, and finally a high of 2 meters. And that's what's shown here is just 2 of those scenarios, and that's for the intermediate low of 0.5 meters and the intermediate high. And again, you can see parts of Alaska and Canada, they won't be affected. Their coast won't be submerged like they will be along the Louisiana, Texas coast or the Atlantic coastline. This is just one example of the types of environments that will be affected by these increases in mean sea level. Norfolk, Virginia, this huge base there, Navy base, the impacts on that have been assessed. And here's another slide that shows how the sea level rise is going to get the whole coastline there closer to the point where flooding begins as the sea level increases through time. And the city of Norfolk has a strategic plan or long-term strategy for dealing with that, protecting those areas that are most important economic engines, considering places where adaptation, like in Louisiana where we raise the buildings above on pilings, or other sorts of adaptation will be required. So hurricanes, I haven't mentioned hurricanes yet. So both the IPCC and our U.S. Global Change Research Program have found a substantial increase in the intensity and duration and frequency of the more intense hurricanes that make landfall along our U.S. coastline. And these are linked in large part to sea surface temperature as these storm systems come off the coast of Africa and drift across the Atlantic and make landfall in the Gulf of Mexico coastline, northern Gulf of Mexico coastline, or the Atlantic. And by late century, our models project an increase in the intensity and the number of the strongest storms. Not necessarily more hurricanes, but the intensity increasing. And and by NOAA's measures, they say by all measures of intensity, the areal extent, wind speeds, storm surge, but if you live along the coastal zone, rainfall. This greater intensity of rainfall is what is causing a lot of the billion-dollar weather disasters that the United States has seen through time. So this is from our most recent National Climate Assessment. These are data from NOAA, and you can see these changes in weather extremes and the number of disasters increasing through time. Billion-dollar disasters, that's the threshold there. So that's for the mainland, but sea level rise and hurricanes also pose existential threats for many Caribbean islands, and not hurricanes in the Pacific, but storms in the Pacific. It's also for Pacific Island nations. And this is one of our images, a satellite image from the Caribbean that shows the before Hurricane Irma in 2017, and this is in the growing season, and afterwards. It looks like it's wintertime in the Northeast, but that's because the islands were denuded of vegetation, and it's very evident in the satellite image. And in addition, let's look at a different impact, and that's landslides. And our USGS, we have a lot of landslide experts, and here shows the concentration of landslides in Puerto Rico after that were caused by Hurricane Maria. And here we have the largest U.S. housing disaster mission in U.S. history, and net out migration. I know your next speaker is going to talk about forced migration in your summer series. I hope to be able to listen to that. And so it's caused a lot of migration, 215,000 net migration, and that's from the Census Bureau, and that's a year later. So it's not just the immediate, but that's a long-term impact on the loss of residents. The entire electric grid failed, and the water, the communication, the roads, you know, they just have to go down in one spot and can affect the whole island. Switching now to examples of impacts. So warmer winters lead to changes in the distribution of plant and animal species, like Chinese tallow, which is not native to the United States, but it's freeze intolerant, and it is everywhere along the Gulf Coast now. This creature here, nutria, was imported by William McIlhenny into Louisiana for its fur decades ago. And today, nutria that were imported are in the Delmarva Peninsula. So they're freeze intolerant. When I was Secretary of Wildlife and Fisheries, we had a bounty on nutria, $5 per carcass, but actually there were so many of them, they just cut off the tail at the end of the animal. They would bring them in, the trappers would get their $5 because their tails freeze and their toes freeze, and but these milder winters are having an impact directly on these invasive species. Lower soil moisture also leads to more intense, frequent, and widespread fires. Here's a marsh fire, lightning ignited, and when you have less runoff to the coast, that's what you get during a dry period. And here we have what's called a brown marsh event down in Terrebonne Parish, Louisiana. And some of our colleagues at LSU attributed that brown marsh event to pest and the impacts of the drought on this that are caused by a higher order effect of invasives and pathogens on the marsh. And a lot of times in Louisiana, when that occurs, it just goes to open water. When you get the nutria will eat the roots of the plants, and it's right at sea level on a very fluid substrate, and it turns to open water. So these are very important for the future of some coast, like the Louisiana coast where I live. As sea level rises, fresh and brackish water systems will become more saline. Ball cypress trees, taxodium, they can only tolerate salinities of 1 to 2 parts per thousand. The salinity of the Gulf is 35 parts per thousand. So this is the effect of the sinking of the land and the rising of the water in the Gulf of Mexico. And here's, this is the Mississippi River right here. And these are the hurricanes that broke, the levees that broke during Hurricane Katrina. And all these little dots here, those are remnant ball cypress trees. The subsidence and the saltwater intrusion here occurred so fast that it couldn't be reoccupied by marsh grass, saline species. It just converted directly to open water. And we call these ghost forests. And you've got them in South Carolina, Florida. As sea level rise and coastal storm intensity increases. You'll see flooding of the coastline. Here's a study that I helped lead for the U.S. Department of Transportation, and everything in this graphic here just shows the transportation infrastructure that would be inundated. And even on a pretty day, I took that photograph there, even on a beautiful day, you can get a southeasterly wind and your roads can go underwater. You know, that may not be the case on the New Hampshire coast at this point, but that's the case along a lot of the Gulf Coast. Low-lying coastal ecosystems will erode more rapidly if storms increase in intensity as projected. This is Dauphin Island, Alabama, and this is pre-Hurricane Ivan. And this is when our staff, a fellow named Abby Salinger, another IPCC author, he used LIDAR. These are houses, and this is the north side, this is the bay side, and this is the Gulf of Mexico shoreline. And each of these houses here, using a tool we call LIDAR, this is what it was like before Hurricane Ivan, and that's what it looked like after Hurricane Ivan. All of that sediment along that shore there washed northward, inland, towards the shoreline and towards the mainland, and the road was covered, and you can see a lot of those structures are now in the water. And this is what it looked like after Hurricane Katrina. It's pretty stunning. I think these pictures say as much as I could in a page of writing. During Hurricane Katrina, and Rita, we had these two storms back to back. 217 square miles of Louisiana's coast were lost to open water in 2005. That yellow line there, that's the pathway of Hurricane Katrina, and everything in red was converted to open water. And this is the Chandelier Island chain here, and it's a remnant of a former delta that went off to the east off the Mississippi. And as the finer material eroded away, you have the sand barrier islands formed. And so that's the barrier island chain, and that's pre-Katrina and post-Katrina there. My parents lost their home. If you go directly north of the Chandelier Islands, where I grew up in Biloxi, Mississippi, they had the car floated in the garage. The sofa floated down the hall. It was amazing. They'd never had water like that. So, and final example, this marine heat wave increase I talked about. I showed you the global increase and the U.S. Shoreline increase or offshore increase in marine heat waves. And these are altering the fish and wildlife distribution and phenology, the seasonal cycles, breeding and so forth of species. And these are just some examples. So here's the heat waves for the Gulf of Maine. I think thought would be of interest to you. And you can see that increase in the number of heat waves, the days with marine heat waves shown here in these red bars. And this is the daily sea surface temperature in the gray, and then the average sea surface temperature shown here in black in the Gulf of Maine, compared to the 1982 to 2011 year baseline. And so you can see the difference. This is from our National Climate Assessment, and you can see the difference in some of the squid and cod and lobster that are projected into the future, increases and decreases. Some species will increase. By 2050, they're projecting, it looks like an increase in squid, and the migration of squid, rather. And this next slide talks about lobster distribution and production. So here we have the biomass of lobster off the East Coast from 1991 to 2020. And then you have the projected change in biomass into the future, the loss of biomass into the future. And lobster, of course, is the highest valued single species fishery in the United States, and it has seen its southern portion of its population decline due to very low levels, to very low levels with warming. So this just predicts changes in the American lobster distribution through time and their abundance, their biomass. So all these are operating together. You can't just have one aspect of this sea level rise operating. All of these forcings are operating together, and so it's difficult and challenging to understand the interactions of these stressors and the tipping points at which land will be lost, at which lobster will move. You know, those sorts of things are difficult, and I've learned in 30 years of doing this sort of research that there are surprises, for sure. This is a photograph that I took of where oysters grow in Louisiana, and this is these stakes here are oyster growing areas, and this is the BP oil spill. And as it hit this, what was left of this marsh, you know, what are the interactions there? You know, we only know by doing science and providing data and monitoring systems what the impacts will be of other stressors combined with the climate change influences. And the risk from these events arise from these interactions between the hazards and the vulnerability or the susceptibility to harm and the exposure. And one of the conclusions of the IPCC reports, and very strongly stated in our National Climate Assessment, is that the risks are greater for disadvantaged people and communities and countries at all levels of development in the United States, not just in the developing world, but also in the United States. So who is at most risk? This is from one of my colleagues who's speaking later today. I hope to hear his talk on my way to Boston Logan online. And here we have the urban heat island effect in Atlanta, Georgia, Houston, Texas, and Minneapolis. And you can see, comparing the median household income here to the temperature, that as the income goes up, the heat exposure decreases. So I really question these figures to begin with, but the science is there, and it has to do with where disadvantaged people live, people in poverty live, flood-prone areas, and areas that don't have as much shelter, and more heat island intensity. Ending with adaptation and mitigation. Adaptation is purposeful actions taken to reduce the undesirable effects of climate change. Mitigation is to reduce greenhouse gas emissions or enhance carbon sequestration. Running through a few examples, you can reduce the non-climate stressor zone coast. When I took this picture years ago, this was marsh, it's all gone now. This is a levee that prevented the over marsh flooding, transfer of sediment and water to the coastal zone. Here, the Intracoastal Waterway, built by the Corps of Engineers for transportation across the Gulf Coast region, is now a mile wide in many places. And the second approach would be to adapt infrastructure. This house was not built. This is after Hurricane Katrina. It was not built to have a blow-away first floor, but that gives you an indication of what will survive. This bridge over Bay St. Louis, Mississippi, was completely inundated, and this is after the Hurricane Katrina. And when they built back, they built it feet above the water levels during Hurricane Katrina. So adaptation, understanding these processes, is really important. In Alaska, this is just a rock revetment shown here of a native village here in the Kivalina, where their adaptation is very different from what it might be here or in California. Increasing the resilience of human and natural systems. I took this picture here looking towards the Gulf of Mexico. There's nothing left today, but the state has this coastal protection program where they're reinforcing the barrier islands with vegetation. This is the city of New Orleans and a flood control structure on a bayou that would have flooded all those folks, you know, if you'd had a Hurricane Katrina style or intensity of storm. Burning the marsh to enhance the desirable vegetation, lots of different ways that natural systems can be adapted. Another, of course, is to retreat. My parents, when they lost their home in Katrina, they retreated inland, about 100 miles. And in some cases, retreat may be the most cost-effective option. This island here, called the Ile de Jean, this Native American community, the Ile de Jean Charles tribe of the, I think it's the Biloxi Chitimacha. Anyway, this is where their native homeland was. They grew corn here at one time, but now it's those ghost forests are all that are left. And so they are planning to retreat. And this is a group of those Native Americans making those plans here. Finally, this factoring of understanding of scientific understanding of the rate of accretion in your marshes. A colleague of mine, Jim Lynch, measuring accretion rates in a coastal marsh in California, looking at how much the marsh can keep pace with sea level rise. This is Timbalera Island here in Louisiana, and the oil company that operates this structures here, these tank batteries, they put riprap all in front of the island, but it prevented the seasonal, of the longshore sediment transport of sand to the shoreline. So understanding the processes that maintain these barrier islands is really key to adaptation. We've got these tools, I'm just going to breeze through a few of these, that we have developed in collaboration with lots of partners, where you can predict and anticipate the impacts of climate change and the exposure estimates, considering all of these different types of variables. And these are being used in California currently. This is just a web page where we can integrate all of this information for policy making. We have a coastal flooding tool. NOAA has a coastal flooding tool as well. And right now it's available for the California area, and this summer for from Florida to up into Virginia for different storm scenarios. And you can look at the areas that'll be inundated. So if you're going to build a highway or repair a hospital or whatever, you know, you can consider what is possible through these different types of models, groundwater impacts, and the saturation of the soils. And then we have this assessment that we've done, a huge group of scientists that looks at the South Atlantic coastline and the impacts of hurricanes and storm surge and sea level rise in all 5 states. And that's the study area. And we use these scenarios and produce these products, and these are all to support policymaking. And this huge team of authors here, Dr. Shirase from Vermont, for example, is one of our partners in that. So there's a lot of logos I could have put on this slide, but this is just an example of the types of products and tools, looking at very precise topographic mapping from the offshore area to the onshore. We look at the changes in the elevation of the land surface, because that will affect what's inundated and their sustainability. We look at groundwater and the impacts ultimately on the projected shoreline under different scenarios of sea level rise. And this is just one example here for Avon, North Carolina. Then we looked at the assets that were exposed. So they used the data from the U.S. Census on the households, the Department of Homeland Security, the County Assessor's Office, to actually quantify the assets that are exposed here. And these are the findings. With 1 meter of sea level rise, 70% of the coastal residents and $1 trillion in property value could be exposed. We talked about climate change and prosperity. That's a real good example right there for the South Atlantic coast. But as I said earlier, we are not helpless, and mitigation or lack thereof will determine the rate of future warming. And this is from the IPCC special report on 1.5 degrees Celsius increase and the difference in the higher scenarios. And you can see here that if the society responds and reaches a point where emissions and contributions to greenhouse gases are reduced by 2040 to 2050 and start the decline, you can see how we can keep it the rate of temperature increase to 1.5 degrees Celsius. Remember, we're already 1 degree there. So 1.5 degrees compared to pre-industrial times. But if society waits until later in the century, the chances of getting and keeping the temperature below 1.5 is much lower. And every ton of CO2 emissions and methane emissions, nitrous oxide emissions add to global warming. And this shows the historical contributions here. These are the contributions, CO2 emissions along the bottom. And this is the degrees Celsius of increase. There's a 1 degree right there. And if you go in these lower emission scenarios, it could stay at 1.5 degrees over pre-industrial. But if you go into these higher emission scenarios, or even mid-range, your outcomes are more like this. And remember, this is just the global average. It's the extremes that are most important, and the extremes will increase as well. So the pathways ahead are some of the answers in this report that the IPCC produced. The only way to keep the temperature increase to 1.5 degrees or less and achieve a sustainable development goals, SDGs, is to decarbonize the economy through emissions reduction, to capture carbon and keep it from entering to the atmosphere via afforestation or the planting of trees and the taking care of trees and other land use change, and direct air capture. And we've got some really important strides are being made there. And so to get to sustainable development goals, it's going to require mitigation and adaptation. And this just illustrates 4 different scenarios, and there were hundreds that were used. And this pathway number 1, emissions peak about now, and then they start to decline, and you can see there's not a lot of offset required in agriculture, forestry, and other land use, or bioenergy with carbon capture and storage. The longer you wait, the more offsets will be required to keep the warming at 1.5 degrees C. I think this is my last slide about opportunity space and climate resilient development pathways. This is from our IPCC report in 2014. We sat around a table in Argentina, and our authors sat and we developed this chart building on this theory of Brockstrom's planetary boundaries, where you have biophysical stressors on human and natural systems, and societal stressors that affect human and natural systems, and the resilient space. And that may be our present day world today, depicted there in this figure here. But into the future, regardless of what endpoint, whether it's 2100, 2070, it's these decision points that will determine if we move to a future with high resilience and low risk, or a future like this, lower resilience and high risk. And it's these decision points here that take you on one pathway or another. And you can note here that once you start making the decisions that lead to this lower resilience outcomes, you never can quite get back to this point. My acknowledgements. Everything I've presented is referenced as best I could, and these are the sources of my material. And I appreciate, like our national climate assessments, for those we have 300 plus authors. And for IPCC, it's even more. So I'm just acknowledging all of that hard work. And these, if you have your camera, you could take a picture of that QR code there and get to the National Climate Assessment and the Northeast Chapter 21. And I presented a lot of information from that, and you can get to that very easily as well. So I sure appreciate your time and your hospitality, and I will turn it back to Pete. Thank you.
Thank you, Virginia. And we'll now take a 30-minute break. I have 10:10, so we'll be back at 10:40. And bring your questions down here. Get the The box is right over here. I'll move it over here. There's also a box in the back. And those on live stream, send your questions through the chat function.
Oh,
I like it. Welcome back, everybody, for our question and answer period. And somebody asked if we could show the last slide, and here it is. There was also a question about 2 slides back, the one that showed the green and red lines leading to a good result and a bad result. And the first question here is, evidence of climate change due to human activity is quite compelling. How do you, sorry, this is not the first question. This is my first question. Evidence of climate change due to human activity is quite compelling. And this is one of many questions we got. How do you educate and convince our legislators that this is the case?
okay, excellent question. There were a lot of questions. I mean, it's good to see them. I don't know the answers probably to most of them, but some I do. And the feedback, that people understand enough to ask a really good question is important to me. And it's regarding the how to deal with the legislative decision-making. That last slide that I showed on the opportunity space and climate resilient development pathways, those decisions that are made by people, and in some cases, your individual decisions. In some cases, it may be your county or the Hanover decisions, all the way up to the legislative scale at the state level and the national level. And then these global decisions, harder to deal with, but there's the Paris Agreement, for example, is an example of a global decision that's been made. And so how to communicate this information to decision makers, and it's by education. I don't think that one thing I found in my history, I used to be Director of Wildlife and Fisheries for the state of Louisiana, and I had commercial fishermen and recreational fishermen all after the same redfish, speckled trout, and so forth. And what I did is I formed a task force of combination of recreational and commercial fishermen, and I had the data. So all my fisheries biologists brought the data to the table, and it was amazing when people had the same understanding of the facts, how easy it was to reach a consensus. And I think it's the same thing on climate. If you have the facts from a trusted source, repeatedly presented, that is the way to underpin decision making. I'm not a policy maker, so I'm not going to recommend policy. I think in a way, if scientists, and there are actually studies that have been done, that when scientists take an advocacy position, we lose our credibility. And so the decisions that are made by policymakers are their decisions. And so giving them the information and then basically hoping that it has an impact. So I've been working 50 years now. And one thing I've learned is that the power of knowledge and understanding and data can't be overstated.
Okay, now the second last slide that said was my first question is now my second question, that showed the various decision points.
Yes.
As to which way. What was some of the specifics about those decision points?
Some examples. Okay, some examples of the decision points in that opportunities pathway. Boy, I remember sitting around the table, developing that and talking about, okay, it could be mitigation or adaptation. So you've got 2 basic options, societal options. One is mitigation, which is either reducing emissions or sequestering carbon, basically. And the other side of the coin is adaptation. And I gave you some examples of adaptation: elevating houses on stilts, building flood control structures, and that sort of thing. So the combination of those, each decision point, and there could be hundreds of, I couldn't even imagine a number on the decision points, but there are your personal decision points, then there are decision points that society makes about the use of certain types of fuels, for example, cleaner fuels, and decisions on the adaptation realm of what kind of structure you build. Do you build a soft, nature-based solution, or do you build a levee that can be breached during a storm? Those are the type of decisions. So there's a wide range of decisions, but they collectively can determine the resilience of either a community, a fishery, a nation, or the world.
Thank you. The science is compelling as well as frightening. Are you, as in the USGS, encouraged by the political will to address the issues?
It varies from state to state, from local to local. In my state, for example, we had a climate task force. And so the governor appointed me as chair of the Science Advisory Council to the climate task force that produced a report with a vision of how to reach net zero emissions by 2050. So for my state, and for at least 20 other states, they have a target of carbon neutrality, net zero emissions by 2050. So it varies from place to place, and just for my state, I was proud to serve on that task force. And we did come up with a plan, but it depends largely on hydrogen fuels. And there's a lot of science and technology and markets that would need to be overcome to get there.
Somebody asked the question, does USGS share this information with China? And I'll add, or Russia, or everybody else in the world.
Absolutely. Everything, we work for you, and all of our information is publicly available after it's been through peer review. Okay, we have very rigorous peer review requirements, and once the information is available, it is available to the public, both the data and the reports. There is one exception. So we have a big minerals and energy mission area in the USGS, and we do assessments of oil and gas reserves. And so when our geologists go into an area like the Permian Basin and they do a resource estimation, we do not release that to the public because it could give, we don't release that prior to it being available to the entire public, because it could give a company an advantage economically, or an individual that might want to go in and buy an oil lease there. So that's the exception. But all the rest of our science is publicly available. I can't think of another, like our volcano observatory information, our earthquake monitoring, our stream gauges. As a matter of fact, a lot of this is available the day after it's real time. Our stream gauging stations are real time, and it's all free. Even our Landsat images. When I started working on this years ago, I had to pay, even working in the Department of Interior, $1,000 a scene for a Landsat image, roughly. And then about 25, 30 years ago, we started making Landsat images free and available to the world. That's what your Google Earth, for example. And China, other countries, they'll download everything. So we deliver this. We have, through our Earth Resources Observations and Science Center out in Sioux Falls, we have the Landsat archive, and it's free for download, and people access it for no charge at all. And interestingly, when we made this data free and open to the world, and we were formerly charging the $1,000 per scene, the Landsat archive had barely been touched. All that expense, going into these satellites, and we've got Landsat 9, the 9th satellite that was launched. The cost of that was not being recovered by the United States or anyone else. It wasn't being used. And the minute we made that free and open available, the use is skyrocketed, as you would imagine. So now it's free and available to the world. And the cool thing is, so when the Europeans were planning their Sentinel satellite mission, we had a signing ceremony where they agreed to make all of their data free and open to the world. So what America did cascaded globally, and we were one of the first countries to have this land orbiting satellite ability.
Thank you. You said that USGS is science and it's data. You don't set regulations,
No,
that type of thing?
no.
Now, you're part of the Department of the Interior, and the Secretary of the Interior is appointed by whoever happens to be the President of the United States. Is there any pressure from the Department of Interior on what you all do at USGS?
Well, we report through the Assistant Secretary for Water and Science to the Secretary of Interior. And, but we have a very rigorous scientific integrity policy, and 20-plus federal agencies have upgraded their scientific integrity policy so that the science that we do is safe from political interference. The products that we produce are safe from political interference. But the budgets and that's still a concern, yes, sir.
If we stop CO2 release, how long would the climatic effect of the existing levels persist?
Of centuries. If you stop the emissions of CO2 and other greenhouse gases, the Earth's surface temperature would continue to warm. We call this the global warming commitment. It sounds like a commitment. That's something that an individual will do. But it's the commitment that we've made by our actions in changing the composition of the greenhouse gases. And there's a commitment that we've made by that action, or those actions, for continued warming. So it will be a long time. And sea level rise effects would be even longer because it takes a long time to reach equilibrium with the temperatures in the atmosphere back to the pre-industrial levels, for example.
What representative concentration pathway scenario, RCPS, is the U.S. Using to determine its climate change mitigation policies? And maybe you could explain what RCPS is.
Yeah, that's the reference concentration pathways. Those are the plausible pathways for development. And so the IPCC doesn't actually do the scenarios, but they use scenarios that are developed by the Climate Model Intercomparison Project. And so we have a lot of agencies in the U.S. government and with our academic institutions that are part of that partnership that produces these model projections. And there might be 25, 30 different institutions contributing. At least there were 10 years ago, and there's probably a lot more now. So for the last IPCC report, there were 1,202 considered options for these combinations of SSPs, shared socioeconomic pathways, with RCPs, and they centered on these 4 or 5. So that those are represented in the 5 different scenarios that I chose, and or not that I chose, but that IPCC chose for their assessments. And then basically for our U.S. National Climate Assessment, we use the same CMIP 6 database, Climate Model Intercomparison Project, number 6, for the assessment reports that we produce. So our reports, the outcomes are very consistent with what the global assessments say.
Is there any place in the world that is safe for me and my extended family?
Oh my goodness. I love that question. Is there a place that is safe? You wouldn't believe how often I get asked that question. I get emails. I must be on some sort of list or something that I get emails, especially in the spring, for students that are doing their papers and wanted me to. I started just having a template, and I'd cut and paste if they wanted to know about CO2 or forest or whatever. And I got one a couple years ago. I've had 2 that were alarming to me, where one was from a young woman, and she and her husband were considering not having children because of climate change. The despair, that people feel. And I think a part of that is from feeling helpless, but we are not helpless. There are decisions that we can make in our individual lives and collectively, societally, that will keep us on a path that avoids catastrophe. And that's what these assessment reports all point to. So I don't want us to lose hope. So where is safe? I've had so many people ask me that. But consider the time frames that I'm talking about here and how long it took to get from 1.7 millimeters per year to 4 millimeters per year, 50 years. So things, fortunately, there are a lot of buffers in the system, and it takes a long time for systems to, some systems to respond, not necessarily lobster. Okay, my response might be quick. So please think of the time frame and decisions. A lot happens. COVID, there are surprises that I mentioned that will affect our emissions and decisions that we can make. And technology, carbon capture, for example, we're just, that's a dream, not economically feasible and presently, but the promise is there enough to where, for a large-scale deployment, it's not economically feasible. It is for certain applications. And in Europe, they're demonstrating a lot more advances in practical applications. So just hold on and let's, make informed decisions and avoid catastrophe. And that's what you do with the information. So where you live, it depends on where you start. There are places in this planet that are going to get drier. I'm particularly concerned with places in Africa. There are islands that are with large populations that have the Marshall Islands, 2 meters average elevation in the Marshall Islands, and that's a protected area of the United States, freely associated. And the communities there, the displacement of people, and so they're more vulnerable. Where do they go? There are island nations that are already talking to, continental-based nations about migration and that sort of thing. Years ago, ambassador from Palau spoke in the Department of Interior building, and his plea, he wept on the stage, worried about his country and his people. So it depends on where you are. And I'd say if you lived in Missouri, versus Plaquemines Parish, Louisiana, is a big difference.
What is the best estimate of what's going to happen in the Marshall Islands in terms of the continued existence of them?
Well, it depends on the pathway and the sea level rise and the storm patterns. And so the freshwater lenses under the islands in the Pacific, very limited in their amount of fresh water. So a lot of implications for the growing of their crops. But again, it depends on the actual outcomes of these various scenarios. And the implications for small island states. At an IPCC meeting years ago, 1.5 to stay alive. And there was island nations that banded together and chanted that, 1.5 to stay alive. And what they're talking about is that 1.5 degree threshold or target in the Paris Agreement. And above that, we're tracking above that, their existence is literally threatened as a nation.
Is there anything they can do to mitigate the onslaught?
Well, you saw the island in Kivalina, Alaska, where they're built the rocks around it. So yes, there are things, flood-proofing of structures, building of new highways. There are many, many examples, but the ultimate inundation of those low-lying islands and atolls, there's some things you just can't stop. And that's a huge concern. That's why the small island states band together, and there's a chapter on small islands, and there's an islands chapter in the national assessment as well. So if you go to that icon there on the right, there's a chapter there, and you can learn about the implications for islands and territories.
Good. Thank you. Forests provide an enormous resource for CO2 absorption. New England forests have significantly fewer forest fires than forests out west. Why? Can anything be done to mitigate the western forest fires?
So the intensity and the size, the aerial extent, and the frequency of fires is highly influenced by drought and soil moisture. So you don't have the soil moisture problems here. Remember the precipitation increasing? You don't have that here compared to the out west forest. And so that's one of the things we do with our Landsat imagery. We monitor forest fires and their frequency and extent, and the trends out west are very different from here, and it has a lot to do with soil moisture and temperature. And the most remarkable trends are in Alaska, where the wildfires have changed so many different types of environments, but particularly in the boreal forest. And so it's the climate. It's the difference in climate, basically.
You've kind of touched on this a little bit, but what areas of the world are more at risk for sea level rise? And what would they be? What would be best, to mitigate or seek refugee status somewhere?
Mitigate or adapt, yeah. Okay, what areas are most at risk of sea level rise? If I had to pick one, that would be deltas, large mega deltas. In our IPCC AR, one of our prior reports, not the most recent, we call them hot spots of societal vulnerability, these large deltas. We have millions of people confined in sediments, relatively young sediments that tend to be sinking with no elevation, no barriers, and so these low-lying deltas, and which are economic engines in many countries. That would be one hotspot of vulnerability. Another hotspot of vulnerability would be the Alaska and Canadian coastline, because of the combination of the decline of sea ice. And so you have a shoreline, and then you have an ice abutting the shoreline, and that prevents erosion. The ice does. And so as the sea ice retreats, you have more erosion just from storms. And plus, in some of the parts of the Arctic, the storms are changing and increasing in intensity. In addition to the sea ice retreating, the permafrost is declining. And a lot of these shorelines are permafrost sediments, and as the ice melts, it collapses, basically. And then, of course, sea level is rising on top of all that. So I'd say the Arctic shoreline, and the rate of change in the Arctic is much more rapid, the increase in temperature, than it is in this part of the world, and particularly where I live in Louisiana.
What are the 2 to 3 most impactful things that each of us in the audience can do to help decrease the warming?
Okay. If I had my last dollar to spend when I was Secretary of Wildlife and Fisheries, or even at USGS, it would be on education. So 2 or 3 of the most impactful things I think that we can do is to understand and to educate yourself. And this is not difficult to understand, in my view. I mean, sorry, I keep hitting this thing, this lavalier. Sorry. So I think education is one of the most impactful things you can do, because when you understand all of these things that are at work, you can't help but have that underpin your thinking and your actions. You know, what kind of car you buy, where you choose to live, what kind of house you build, who you vote for. You know, I mean, it permeates your being. When you know something, it informs your decisions. So that is probably the most impactful thing, because as a basis, or understanding the basic science, you can take personal actions and expect larger scale actions from your community or your government that would lead to a more resilient future for you and your children. So After you get over the education threshold, then it branches out into thousands of decisions. What kind of light bulbs you use, you know, what kind of transportation, public transportation you use. Just multiple decisions beyond that point. I love EPA's websites on what you can do as an individual to offset the carbon emissions.
Along the same line, somebody asked, which generates more CO2, a gasoline-powered car or the electricity you use to charge your electric vehicle car?
That's a hard one, because I'm not an engineer by any means, but from my understanding, and you drive an electric car,
Yes.
so you probably know more about that answer than I do.
I don't have a PhD, though.
Oh, no. But I'm a coastal ecologist, but that question comes up a lot, and the net influence on greenhouse gas emissions is less with the electric vehicles, simply stated.
Particularly if you're using renewable energy
Yes.
to generate your electricity.
Right, right.
Can you comment on international adaptation and mitigation, and Bangladesh being an example?
Okay, so I represent the United States on a lot of international committees. I'll be in Ecuador next month, and I work for the Office of International Programs at USGS. So international examples of adaptation or mitigation, which one? Adaptation, I believe. Both. Okay, of climate response strategies. Yeah, so it varies, and it has a lot to do with the development status. A lot of countries don't even have a climate assessment like we have. Most countries don't have. I mean, a lot of the Europeans do, but you know, starting with the basics on which to make decisions. Otherwise, you're more of a reactive mode, as in Bangladesh with flooding. But Bangladesh had a champion, Salim Huq, who was an IPCC author with me a couple of times, and he passed away recently, but his impact on Bangladesh is incredible. So I represent the Department of Interior on this Climate Security Roundtable of the National Academies of Science, and we had a contrast. We did a workshop on climate change in Southeast Asia, and Salim, Dr. Huq, spoke about the Bangladesh experience, and then we had the Pakistan flood experience. I mean, night and day, because of the information that they had, and they built on experience to where they built places for people to retreat during flooding, and so people didn't die as a result of the storms that were hitting Bangladesh. So I'd say there's a lot of lessons to be learned from Bangladesh. Hurricane Sandy that struck the Northeast, the lessons learned there. I was at a Cities Forward conference last month, and the State Department has these paired cities, a U.S. city with a South American city, and the mayor of Hoboken spoke to us, and he presented his examples of how they have adapted to flooding, and his partner is Montego Bay, Jamaica. Remember the hurricane that just came through here and the impacts there. So there are wonderful examples of nations supporting one another, and I think that's very encouraging.
You've also somewhat addressed this question, but I love the question itself. Your roots are in Louisiana, with the land sinking, the sea rising, the gas and oil companies powerful, and the voting majority Republicans. I view Louisiana as perhaps the softest of the soft coastal underbelly. Yours is a global perspective, and the IPCC has it clear, but have you direct experience with elected officials in Louisiana?
I am married to one. And it was a crazy, my husband is a district attorney, an elected district attorney for 40 years. He's younger than me. And that's how I met him, was through, I was on their case, DA's case about wildlife and fisheries violations. But anyway, So in Louisiana, the soft underbelly, that's an interesting term. Soft coast is more accurate, I think, or is an accurate description, because all of that is deltaic sediments. All of Louisiana's coast was formed during the Holocene. Remember I showed the graphic that had the temperature change, and then you have the past 10,000 years, very little change. Sea level has been stable, and that's when coasts, as we know them today, were formed. That's when the Louisiana deltas were built. And the Mississippi River is like a big hose spewing out sediment and fresh water, and it'll build up land one place, and it's easier to change course and go to a different place, like the Chandelier Island chain. And then when it abandoned that delta, it eroded away and it formed a different delta. So Louisiana is soft. It's young. Our sediments, 54% of the state is geologic floodplain. And regarding the politics of it, as I mentioned, we had a climate task force, a governor's climate task force that developed a net zero emissions policy. And that's kind of where I have to step back. I'm not a policymaker. I was back when I was with Wildlife and Fisheries, but that was 30 years ago. And from a scientific standpoint, and as a scientist, particularly for a government scientist, presenting the information that's where you turn it over basically to policymakers and to an informed citizenry. So I speak a lot and travel a lot to talk to college students and NGOs and partners around the world, and sharing information, I think, is I just have to be confident that people will make the right decisions.
Good. What's been the effect of climate change on agricultural productivity to date, and what is projected for the future?
Okay, so agricultural productivity is highly dependent upon temperature and rainfall. And if you go to that icon on the upper right, there's a chapter in the National Climate Assessment about agriculture, and there are winners and losers, okay? So as the temperature increases in the northern climes, you're going to have the longer growing season. And so US-wise, it depends on the crop and the location, okay? Food security is another important topic, this National Security Roundtable that I mentioned earlier. So food security in Africa is endangered, terribly endangered presently, okay? And we have what was called the Famine Early Warning System Network, where we use remote sensing and field data to look at everything from the ability to transport food to the ability to store food, political unrest, all those factors. And we send an alert out through the Famine Early Warning System Network that is paid for by USAID. And we have many examples of where a warning would go out, and then the aid community globally would come in and provide the aid to prevent famine, starvation. You may remember Sally Struthers in the 70s on television about the starving children in Africa. That event, I've forgotten what year it was. The Black Caucus, the Congressional Black Caucus, got together and said, we can never allow this to happen again. And that's how FuseNet came about. That's just one of the responses. So again, there are decisions that can get you to that resilience and get you through a famine. And hopefully you learn from those events.
Thank you. Somebody wrote, about 15 years ago, we visited Costa Rica in a farm totally powered by methane produced by cow manure. Are you familiar with this? Is it still being used there or elsewhere?
In Costa Rica, I was there 2 times the past couple of years, and I didn't personally see that sort of thing, so I can't attest to whether it still exists or not. But I know it is common in the developing world for the harvesting of methane from livestock. I was in China years ago, And it was interesting that their swine production is done in-house, literally. Okay, so in the homes that I visited, they would have, and a lot of them were like cinder block homes, and they would have a place where they would feed their swine, their pigs, and they would have a methane capture and a little pipe that would go up to the burner upstairs that they used for cooking. So it's I'm sure it's still around. The need for it or not, it would vary from country to country.
Is the impact of climate change and reduction of the ice sheet as significant for Antarctica as for the Arctic? Would this have a different impact in different hemispheres?
That's a complicated question. And so the U.S. National Assessment, we don't deal with the Antarctic ice sheet decline. But if you'll recall, I had a slide about I think it was 7 to 11% increase in the rate of Antarctic decline, but a faster rate of decline of the Greenland ice sheet. And I think the focus in the short term is more on the Greenland ice sheet, but I'm not sure how else just to point you to the IPCC reports, or whoever asked that question, my email address is right there, and if you would email me, I'll get you the facts from the IPCC report to make it easy for you.
What's the effect of melting glaciers on the Gulf Stream?
Again, I'm a coastal ecologist, and I couldn't attempt to give you the numbers. I love to use statistics when I can, and I don't have those handy, but I can answer it online.
Is there a case can a case be made to try to remove CO2 from the atmosphere, as opposed to is carbon capture realistic?
Yes, so this direct air capture is one of the 7 negative emissions technologies. The National Academies produced a report on negative emissions technologies led by Stephen Pacala from Princeton a few years ago, and they came and talked to us, the leadership of the U.S. Global Change Research Program. And this carbon capture, direct air capture, basically it's turning things in reverse. Instead of emitting, you're extracting. And they had these 7, so afforestation, or trees, were planting trees, maintaining forest was one of them. Direct air capture. There's a whole series of options. And there was an announcement recently about a direct air capture, a huge plant, it'll be the biggest in North America, that was just funded. So you see more of that in Europe than you will here, but it is a promising sort of approach, and that, again, hydrogen fuels are another, those are the deal breakers, the things that could really reset the dial, and the fears that our younger generation has about their future. If it's like that National Academies report and the 1.5 degrees C report, the urgent need for technologies. And just imagine the impacts of making it feasible for direct air capture. And a good example, I think, is if you look at transportation in how fast that can be taken up. Transportation in San Francisco. There's a great photograph of horse and buggies. I mean, just not that long ago. And how quickly the automobile took over. It was like flipping the switch. So can we flip the switch with technology?
Where in the world is mitigation the strongest, and where is it the weakest, and where is the U.S. in all of this?
Okay, again, I would have to point up. So U.S. emissions are declining. They have been declining. And that's from EPA. That's from our reports every year to the UNFCCC So there's a lot of progress being made, but where in the world, I'd have to go to the IPCC tables and look, or the UNFCCC tables. I don't know the answer.
To what extent does federal insurance on homes encourage people to stay or move to flood-prone areas?
I wrote an article about the National Flood Insurance Program years ago and the repeated flood insurance claims. And a lot of those were hurricane related. And basically, the National Flood Insurance Program was subsidizing no adaptation, just rebuild as you did before. You know, when my parents lost their home in Katrina, excuse me, someone bought the house and kind of rebuilt it and paid a huge price, but the slab's the same. So they rebuilt right there. So the National Flood Insurance Program has been, the policies have changed, and the 100-year flood view that you had years ago was no longer what we call a 100-year flood, because you saw the charts of the increasing intensity of precipitation. So the National Flood Insurance Program has changed a lot. I'm not an expert on it, but I did write a paper pointing out these repeated flood losses in the same structures 3 times in some cases. And I think policymakers have responded to that information.
Our last question is, once again, USGS does science, now policy or politics. Have your reports or documents ever been pulled from your website for whatever reason? or kept from being put out?
Yeah. I don't know to what, my personal science reports are broadly, in the public. The presence, the web presence does change through administrations. Yes, sir. But the communication of our science is done through, like if you do a search on USGS materials, everything is still there. You might just have to, even today, when there's such an emphasis on getting the science out, you still might have to dig, but it's still available publicly. And I don't think there's anything that we have done other than increase the access, public access, through different search tools, and we've taken advantage of technology to enable people to get directly to information as quickly as possible, unfettered.
Well, Virginia, it's been a delight having you here today, and thank you so much for all the information and helped us with our adaptability and mitigation.
Thank you.
And a reminder that there'll be the post-session discussion over in the OSHER office at 11:45, and we'll see you next week.